If you look at the core of traditional computing, you'll find a strictly rule-based system. A machine receives fixed instructions, and it executes them. In a traditional setup, every action the machine takes requires a human programmer to sit down and explicitly write code for every single scenario it might encounter. If a scenario isn't in the code, the machine simply fails. The boundary between standard programming and what we call artificial intelligence is crossed the moment that requirement for manual instruction is removed. Artificial intelligence is defined by a machine's capability to ingest data, autonomously learn patterns, and make predictions, without ever being handed a step-by-step roadmap. True artificial intelligence begins exactly where rigid, human-coded rules end. The term AI gets thrown around to describe everything from an automated thermostat to self-driving cars. Because it is used so broadly, it creates confusion about the actual levels of computational autonomy. This diagram shows the architecture stack of the field. It is a nested hierarchy. The broad outer shell, artificial intelligence, encompasses any machine mimicking human cognitive tasks. Within that shell, you find machine learning, and nested even further inside is deep learning. As you move deeper into these inner circles, the system's reliance on human intervention steadily decreases. Correctly identifying which architectural layer a system uses is essential to understanding exactly what it can do and where its limits lie. Before an algorithm can learn from its environment, it first has to be able to perceive information. Algorithms ingest reality through three distinct input domains: data science for numbers, natural language processing for text and speech, and computer vision for visual resolution grades. The vast majority of the data flowing through these domains reflects the real world, meaning it is messy, unstructured, and lacks organizational formatting. This visual breaks down the contrast. On the left, you see unstructured text data, raw sentences and paragraphs. On the right, you see that same information formatted into a highly organized, structured data table. AI systems have to translate those unstructured paragraphs and code into clean rows and columns, like the ones on the right, to actually perform calculations. Regardless of the domain, whether reading text or looking at an image, all machine perception relies on translating the physical world into structured mathematical formats. Once that structured data is prepared, machine learning acts as the engine that processes it. To illustrate how this engine works, imagine a hypothetical sorting problem. We have a set of different physical items that need to be categorized into their correct groupings. Machine learning handles this through a process called manual feature extraction. It acts as a necessary filter between the raw items and their destination. In this setup, a human engineer is required to manually define the exact characteristics the machine needs to look for, like size, shape, or color, to sort the items successfully. During the routing phase, the machine uses these human-defined parameters to process the data and place the items into their correct categories. The machine learns the most efficient way to route the data based on repetitive trial and error, but it is not inventing the categories itself. While machine learning exponentially scales processing speed, it remains permanently bottlenecked by the programmer's ability to manually define those physical features. Deep learning and artificial neural networks serve as the architectural evolution designed specifically to bypass that manual feature extraction bottleneck. The functional difference is that deep learning models autonomously extract their own features directly from raw data. This diagram illustrates the structure of a deep neural network, mapping out the connections between its input, hidden, and output layers. It starts at the input layer. This stage receives raw, unstructured image or text data directly, without requiring any human to pre-sort or label the features. The data is then pushed into the multiple hidden layers. Here, information is passed along the network only if the output of a specific node meets a strictly defined mathematical activation threshold. It is inside these hidden layers where the machine autonomously discovers implicit characteristics and patterns without any human instruction. Once processed, the data finally arrives at the output layer to deliver a completed decision or prediction. By removing the need for manual feature extraction, deep learning shifts the burden of understanding data characteristics entirely from the human engineer to the machine itself. Choosing between these architectures requires looking at practical trade-offs. Autonomy is not free. Here is a direct comparison of machine learning and deep learning workflows. Because machine learning divides tasks, It functions well on smaller datasets and standard hardware. Deep learning has an immense computational cost, requiring massive datasets and high-end processing machines. This is because deep learning is an end-to-end solver. It processes the entire problem simultaneously, rather than breaking it down into smaller, manageable pieces. Advanced cognitive computing is strictly gated by an organization's access to massive datasets and premium hardware. That extreme autonomy introduces a serious ethical and practical dilemma. It creates what scientists refer to as a lack of explainability within complex cognitive computing models. Because the hidden layers operate autonomously, it becomes nearly impossible for humans to audit exactly how a machine arrived at a specific conclusion. When these models handle critical functions like healthcare diagnostics, financial policy, or facial recognition, the inability to trace their logic presents a severe real-world danger. This brings us back to the core relationship between humanity and the tools we build. The future of artificial intelligence depends on building autonomous systems whose internal logic remains fully transparent to the people who rely on them.